Hi, everyone. So I've had a handful of friends and family ask me to explain transformer attention, and I actually wrote this blog post on it, but my goal for this video is to walk folks through this blog post, explain some of the terminology, and the hope is that by the end of the video, you'll have a first principles understanding of the transformer attention mechanism. There are existing videos and tons of tutorials online that explain transformer attention at a high level, in the sense that you can interpret the weight matrices as change of coordinate matrices into a key space, a query space, and a value space. The transformer attention operator computes similarity scores between keys and queries, and it uses those similarity scores as weights to construct a linear combination of the values. That's a decent high level understanding, and that's fine as an abstraction. But if you were to derive transformer attention from first principles, then there are still many ways to do it, even under the constraints that you want to compute similarity between the most recent token and all other tokens that you've seen so far. So in this post, I'm going to walk through how you might derive it from first principles. There's obviously a lot of ways to skin a cat, and there are other ways to derive the attention operator, but this is one way that I find pretty intuitive. So I'll start with some terminology, and I'm assuming that people are already familiar with the basics of transformers. If you're not, then I recommend Karpathy's videos. He goes through tokenization, and he walks people through how to construct their own version of GPT-2 or GPT-3. So I'm going to skip some of the history related to RNNs because I want to get right into the problem statement that's relevant for transformers. And the idea is that you want to produce the next token, and that token is somehow a function of some subset of the tokens that you've seen so far. There's information within those tokens that you've previously outputted or seen, and we want to take that relevant information when we produce the next token. So what that suggests is that every token I has some relevance to every other token j. And we want to take those relevance scores and use that to construct some final output, which is the output of the attention operator. So that's what these paragraphs are doing here. I'm just defining that scalar relevance function between tokens I and tokens j. And we're not actually operating on tokens here, we're operating on embeddings, x sub I. And embeddings are just one-to-one with tokens. You can think of them as an alternative to one-hot encoding. And then we take that scalar relevance between each token I and token j, and we pass it all to g, which is our attention operator. And that will give us y sub I, which is the attention output for token I. So this is a little bit of a dense way of writing the notation, but I is constant within this set. So we're computing the similarity between each token x sub j, or each embedding x sub j, with the single embedding x sub I. And we're passing it all to g because it's going to need that information to produce the attention output. So now the question is, how do we make a g more specified? G has some inputs, it has some output, but we don't really know the form that g takes on. So we have to start enforcing some constraints. And one constraint that attention makes is called the deep sets constraint, which is that the order of the embeddings that are passed in does not matter. It doesn't matter if you swap x sub 2 with x sub 1, because ultimately we just want to get the final output of attention, which doesn't care about the order. It'll just be some composite information vector that represents all the tokens that we've seen, regardless of the position that they were located in. And the deep sets theorem tells us that we can decompose g into this specific form, which is actually fairly constrained. It's some function, which we call rho, which takes in a sum of some other function, phi. And the summation is the part that makes it position invariant. You can obviously change any of the terms in a sum, and because summation is commutative, that doesn't change the result. So once you've passed that summation to rho, g has no way of knowing whether x sub I was in position 1 or position 2. So this is a way of expressing permutation symmetry, or positional invariance within our definition of G. This is the first assumption. This is maybe a misframing because ultimately the attention output is put through some linear transformation, but you can also view that as a separate step. So within the context of this attention explainer, we view rho as the identity function. That keeps this pretty simple because now G is just the summation of a bunch of outputs of phi. Now we need to specify the structure of phi. Phi is a function of two inputs. That's confusing. So if we could somehow get it so that phi were just a function of one input, or maybe phi were the product of two univariate functions, then that allows us to further constrain the problem statement. So this is the assumption that's imposed here, which I call relevance contribution proportionality, which is that if a token's relevance increases by k times, then its contribution to the final output of the attention operator G should also increase by k times. Given that this is a summation, that element of the summation should be k times greater. This is a formal expression of what I just said. So if the scalar relevance is k times greater, then its contribution to the summation should also be k times greater. Of course, we could have picked something else that allows us to factor phi into two univariate functions, but this is a very simple way of doing it. And given this assumption, like I mentioned, you can factor phi into two univariate functions. One of those functions is the scalar utility, and the other we'll call v. V is a function of x sub j, which is the quote-unquote other token that we're comparing to our embedding x sub I. Right, now the question is, what does v look like? And we simplify the problem. We say that it's just a linear change of coordinates. So like I was saying at the beginning of the video, you can think of these weight matrices as change of coordinate matrices. So we're just taking the embedding x sub j and we're changing it into value space. Ultimately, the output of the attention operator is going to be some linear combination of those value vectors. So this is just a practical note, which is that when you're computing U, so that scalar relevance score, you're going to compute it across a lot of tokens or a lot of embeddings. That means that you want some form of efficient computation. That lends itself to GPU methods like summation or multiplication, dot products, matrix multiplication. Those are the types of things that are really quick on GPUs. So what this is implying is that this is likely going to end up being a dot product. There are, of course, a lot of other operators that could be used, like linear projections. There are other types of reductions, like I mentioned, like sums. In practice, this does end up being a dot product. And that's what I go into for assumption 4. So U is a function that takes x sub I and x sub j, which are two embeddings, and we want to compute the similarity between them. We want to use something that's GPU friendly. We end up picking a dot product. And we could, in theory, just directly compute the dot product between x sub I and x sub j. That would be valid. To add additional expressivity, we allow those vectors to also go through a change of coordinates. So we call it the query vector, which is just x sub I multiplied by some change of coordinates. And we have the key vector, which is x sub j times some change of coordinates. And ultimately, U is just a dot product between those two vectors. So at this point, we've decided on the general form of U, which is a dot product. But the catch is that we only care about the relative scores between x sub j and x sub I versus x sub j prime and x sub I. We don't really care if all the values are 10 times larger. So that speaks to the fact that we likely want to normalize the values of U. There's a lot of different types of normalization. In practice, we use softmax. Softmax is the normalization that attention transformers uses. And that also leads to another normalization, which is that we divide by the square root of the dimension of the embedding space. The reason for that is that the dot product is a summation between the product of each of the coordinates of q and k. So if the dimension is very large, then that means that the summation will also be very large. When you have really large values, then that tends to saturate softmax, meaning that the largest values get almost all of the weight, and we don't want that to happen. So in practice, we divide by the square root of the dimension of the embedding space, which is the correct value if you want to keep the variance of the summation to be a constant. So this gives us the final form of the attention operator. This is, in general, how it's expressed. Sometimes you might see x first and then the weight matrix after x, but you can, of course, take the transpose of that, and that will be equivalent to this single vector operator that I've defined here. So we made a handful of assumptions along the way, but we didn't have to actually pick those specific constraints. We picked some of them for architectural reasons, we picked some of them for algebraic reasons, but you can imagine alternative attention operators exist. And they do. There have been many attention operators that have been postulated. People have tested them. Some are more performant than standard transformer attention. Many of them are less performant. In practice, we stick with this mechanism because it works in practice. But there were some constraints that we couldn't choose. For example, the deep sets form. If you want it to be permutation invariant, you're going to end up with a deep sets form for G. For example, if you wanted to have some kind of normalization, you're likely going to end up with softmax, Gumbel softmax, one of the standard normalizations that people use. So there's some wiggle room. There's some things that we obviously could have changed, like the linear change of coordinates. That's GPU efficient, so it makes sense. There might be other types of change of coordinates that more accurately reflect the actual key space and query space. So these are the types of changes that I'd be interested to see people play around with. I have my own ideas around what an alternative attention mechanism might look like, and I hope that this video was helpful for those who are trying to better understand how attention works.